Hello. So, in this particular chapter, we are going to start now looking at reacting mixtures and the concept of combustion. The objective of this chapter is to look at systems that involve chemical reactions occurring with a emphasis on the combustion of hydrocarbons. Hydrocarbons being a series of molecules that predominantly are made up of hydrogen and carbon. However, these hydrocarbons could also have embedded oxygen, such as some of the alcohols. And with that in mind, the hydrocarbon itself could also consist of some oxygen atoms. And so we will keep an eye out on that also. Basically, the principles that we'll be looking at in this particular chapter are the same as we have in thermodynamics. We'll be looking at the conservation of mass and energy, as well as the second law of thermodynamics. We will be evaluating the enthalpy, the specific enthalpy, the mass-based enthalpy, the mass-based internal energy, as well as the mass-based entropy. But in this case, though, we are going to have to account for the fact that some molecules will actually disappear when the combustion occurs with the opening up or the beginning of some other molecules that may not have been there. So we're still going to be looking at flowing systems and conserving mass and energy, and also writing the second law of entropy production or entropy accounting. But now we have to concern ourselves with, as we go from one state to another state, the same species, the same components of the mixture may no longer be the same. And so once we finish this, we'll then be looking at the concept of equilibrium as well as dissociation in the next chapter. Okay, so in introducing this concept of combustion, when a chemical reaction occurs, and a lot of this should be familiar to you from a course in chemistry, what's happening is the bonds within the molecules of the group of molecules that are going to react or going to combust. That group of molecules are called the reactants, and those bonds are broken, and the various atoms and electrons associated with those reactants are going to rearrange themselves into a series of new molecules called products. In combustion, the rapid oxidation of the elements of the fuel result in an energy release as the new combustion products are formed. Now, reactions occur all the time, okay, but in this particular case, when we talk about combustion, the word combustion is typically related to a group of molecules that react with oxidizing type of molecules to allow or to permit the release of energy. And so that is, when we talk about combustion, we will keep that in mind. The main components, the main chemical elements in most common fuels consist of carbon and hydrogen and possibly some sulfur. And again, we also might have some embedded oxygen in some of the fuels. And in essence, what we're going to be looking at is a series of these chemical elements making up molecules that we'll call the fuel that react with oxidizer type of molecules. And so our reaction that we're going to be looking at is fuel plus oxidizer, then the combustion event producing products of combustion. And so the oxidizing species will join with the fuel atoms to form products that contain those fuel atoms and the oxidizer atoms, with a subsequent release in energy as the bonds break and new bonds are actually formed. And so in thermodynamics, we always talk about a process going from state 1 to state 2. Now our process is going to be state 1, which is the original state of the fuel and the oxidizer, and state 2 will be the final state of the products, and during that process, heat will be released from the system. And so the bottom line then corresponds to, first of all, writing balanced equations representing the conservation of atoms in the fuel and the oxidizer, and how atoms cannot disappear, but then they'll show up in different molecules in the products, and also being able to determine the energy, the flow energy of the fuel and the oxidizer by knowing something about their enthalpies, and then how the enthalpies of the products then will give rise to a difference associated with the heat release. So when we have a chemical reaction, mass is conserved, and the mass of the reactants must equal the mass of the products. There's no disappearing or no production of new mass occurring during the combustion process. When we start doing these types of problems and we start looking at the various molecules, and we typically refer to the molecules or the atoms being a certain number associated with the molecular weight or the moles, the number of atoms or molecules. As we look at these systems, moles are not going to be conserved from the reactants to the products, but atoms will. And we'll talk a little bit more about that here. And so we will be referring to the stoichiometric coefficients. The stoichiometric coefficients are basically the numbers that are associated with the moles of each of the individual components or species, and how those stoichiometric coefficients will help us balance the atoms from one side to the other. So here's a very quick, easy example of a complete combustion of hydrogen with oxygen. In this case, we are looking at 1 mole of hydrogen gas. Typically, we don't write this subscript G for gas, it's inferred. And then with 1/2 of a mole of oxygen, again, we don't write the G, inferring that oxygen is a gaseous species. And they react together to form 1 mole of water, H2O. So in this particular case, we can immediately see that this 1 mole of hydrogen and 1/2 a mole of oxygen corresponds to 1.5 moles of molecules associated with the reactants. And since 1 mole of molecules is equal to a certain number, we see that this corresponds to a certain number of total molecules. And as the reaction occurs, what happens is the molecule itself turns into a larger molecule, and we see that the conservation of atoms will allow us to say that only a single mole of water is formed, even though we had 1.5 moles of reactants. And so this equation is stoichiometrically balanced. And what we see is moles are not conserved because we have 1 plus a half being equal to, and the arrow just indicates the direction of the reaction. We can think of that as an equal sign, and so 1.5 moles does not equal 1 mole. But when we look at it on a per atom basis, we have atoms that represent, or we have molecules that are represented by 2 atoms together. And this oxygen is a molecule that's represented by 2 atoms together. And so when we start looking at and accounting for atoms, we do see that 2 atoms of hydrogen combine with 1 atom of oxygen, because a half a mole of oxygen would be the same as thinking of it as 1 atom of oxygen, then forms a single molecule that has 2 atoms of hydrogen and 1 atom of oxygen. And so as we read this equation, we basically can say that 1 kilomole of hydrogen gas reacts with a half a mole of oxygen gas, forming 1 kilomole of H2O. In the English set of units, we talk about pound moles, which is again a number associated with a certain number of these molecules. And so on a pound mole basis, it's still 1 pound mole plus 1/2 pound mole is equal to 1 pound mole. If we were to take each of these equations and represent these equations in terms of mass, what we see is 1 kilomole of hydrogen gas actually weighs 2 kilograms. Because of the molecular weight of hydrogen gas. This 1/2 kilomole of oxygen is actually 16 kilograms, because an O2 molecule, there's actually 32 kilograms in a kilomole of oxygen, but we only have a half, and so we see that we then have 16 kilograms of oxygen, and then that forms the 1 kilomole of water, and 1 kilomole of water weighs 18 kilograms. And so we see 2 plus 16 is equal to 18, so we do have a balance. When we talk about pound moles, instead of kilograms, we have pounds. And again, the same formula occurs on a mass basis. 2 pounds of H2 plus 16 pounds of O2 would then form 18 pounds of water. Now let me just remind you at this particular time, what is a kilomole? What is a pound mole? Well, one of the things that you might have remembered, from your chemistry class is there was something called Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23rd particles. And 6.02 times 10 to the 23rd particles of carbon actually weighs, and so if we had the carbon atom and we had 6.02 times 10 to the 23rd carbon atoms, that would weigh a total of 12 grams. Okay, so that would represent one gram mole of carbon atoms. A kilomole is the same thing as 1,000 of those gram moles. And so if we had 6.02 times 10 to the 26th of these carbon atoms, they would then weigh 12 kilograms. And so when you think about a mole, the definition of the mole is primarily based on the gram mole. And so if you just hear mole, they're usually referring to the gram mole. And again, the gram mole is reference to 12 grams is a full gram mole of carbon. And so that's how we then get this. Now, what is a pound mole? Well, a pound mole then, one would have to compare the 12 grams to 2 pounds. And when you do that comparison then, since 12 grams would be equal to 6.02 times 10 to the 23rd, then when you compare those 2 grams to 2 pounds, then you could say, well, then, therefore, there is that many more atoms associated with a pound mole. And so one would have to make sure that you understood the difference between the different masses and the differences between the gram moles, the kilogram moles, and the pound moles. But in our particular case, when we write our balance reaction, we're really only interested in balancing atoms, and the stoichiometric coefficients are going to be the number of moles for each of the individual species. And those moles could either be kilogram moles, gram moles, or pound moles. In discussing combustion, our fuel, what we call is a fuel, is the combustible substance, and it's usually a hydrocarbon type of based substance, such as something that has hydrogen and carbon and maybe a little bit of sulfur, maybe a little bit of oxygen associated with it, and it can either be in the solid, liquid, or gas form. Coal is another fuel that is primarily made up of carbon, sulfur, hydrogen, nitrogen, and oxygen, and we have to represent that on a mass basis, determine how much of each of the components. We would go through an analysis to present that. Usually it's very heavily on the carbon side. And then these are typical fuels that then get oxidized by air, let's say. And air is one of the oxidizing agents. Pure oxygen is also an oxidizing agent. What air really is 21% oxygen and 79% nitrogen. And so oxygen is the species or the component that's actually performing the oxidation or the combustion on the fuel. In the case of burning something with air, the nitrogen just kind of goes along for the ride. Okay, and so when we look at air, we basically can say that for every mole of oxygen, we have 3.76 moles of nitrogen. And so when we write the air coming in as the oxidizer, again, the stoichiometric coefficients are always in this particular ratio. And as I said, nitrogen just goes along for the ride, and what nitrogen was there in the air just shows up on the other side of the combustion arrow as just being nitrogen at an elevated temperature because of the heat release. Now, at high enough temperatures, we know that some of that nitrogen can actually react and form other species. And so we will see that when we get into chapter on equilibrium later. When we designate how much of each of the two components we have, again, air being the oxidizer and fuel being, air being the oxidizer and fuel being what is actually being oxidized, we can define an air to fuel ratio on a mass basis. And on a mass basis, since we write the equation typically in terms of moles, we need to know the molecular weight of both the air and the fuel. And so those molecular weights will be known. For air, the molecular weight is 29 approximately because it's primarily nitrogen at 28 and oxygen at 32. And then depending on whatever the hydrocarbon fuel is, we have a molecular weight associated with that. So we can write the mass the air to fuel mass ratio in terms of the air to fuel mole ratio of the air and the fuel. This mole ratio is typically given by the symbol AF with a bar over it. The bar stands for on a mole basis, and the AF without the bar is on a mass basis. And so we see the relationship between the two is just the ratio of the molecular weights. So how much air do we need to burn a fuel? Well, we can begin by saying that there is a theoretical amount of air that's required, and that theoretical amount of air is just enough such that all the oxygen causes the carbon in the fuel to turn into CO2, all the hydrogen that's in the fuel to turn into water, all the sulfur that's in the fuel to turn into SO2 without any O2 remaining. And so when we get ready to set up the stoichiometric equation and the subsequent actual equation for the burning process, we need to calculate this first. So as an example, let's try to determine the theoretical amount of air that's required for complete combustion of methane with air. And so we're going to write that then in a stoichiometric equation. And we're going to start with 1 mole of methane. And we're going to say that we want a certain amount of air. And again, air can be written as 1 mole of oxygen along with 3.76 moles of nitrogen. And now in this particular problem, we put in a constant A because we're wanting to solve for that. And we know that complete theoretical combustion requires that all the carbon that's in the fuel must turn into a CO2. And all the hydrogen in the fuel must turn into water. And all the nitrogen just goes along for the ride. And so by bringing in an A and a C, an A, a B, a C, and a D, we can now write 4 atom balances to solve for A, B, C, and D. And by coming up with those appropriate numbers, we then balance all the atoms on one side to be equal to all the atoms on the other side. And so in this particular problem, you just start by looking at the equations, and you see that this carbon has to turn into a 1 carbon here, so you can immediately say that B is equal to 1. Okay, so the next thing is you look at the hydrogens, and we have 4 hydrogens, and they then form C waters. And so since there's 2 hydrogens in a water molecule, we can then immediately say that C is equal to 2, because 2C plus it has to be equal to 4. Now that we know B and C in this equation, we can now say that B times 2 plus C times 1, B times 2 plus C times 1 has to be equal to 2 times A. And so we are taking these that are known and coming back and determining what the constant A must be. And so that equation holds. And so we see from here B is equal to 1, C is equal to 2. And so then we would have, in this particular case, we'd have 2 times 2. 2 times 1, which is a 2, plus another 2 has to be equal to 2A. And so by doing that, we find that A is equal to 2. And then the nitrogen, again, is just kind of going along for the ride. So once we calculate the value of A times 3.76 has to be equal to the D. And so this 2 times 3.76 then is the value for D. And so our balanced chemical equation for the burning of methane stoichiometrically, theoretically, with no oxygen left over, is then simply this equation right here, 13.4. Now that we know that, we can now determine the air to fuel ratio on a mass basis, and we know that that's equal to the air to fuel on a mole basis times the molecular weight ratio. So what is the air to fuel on a mole basis? We come over to here and we see that we have 2 times 1 plus 3.76, and so this is 4.76 times 2, and so we see that that's 9.52. And so 9.52 for the air to fuel on a mole basis times approximately 29 divided by 16, which is the molecular weight of the methane, then is equal to 17.19. So we have 17.19 kilograms of air for every kilogram of fuel, or grams or pounds, whichever unit system that we want. And again, that would then correspond to the 100% theoretical air. But then if we say we want to have more than theoretical air, we then say that we may need 150%. And so if we call out for 150%, we would multiply this by 1.5. And what that would do then is, in this equation here, that 2 would go up to a 3. And so we would then have 50% more oxygen than what we need. And so that would correspond to 150% theoretical air. And so if this goes up to a 3, then what happens is there's going to be an extra oxygen over on the right-hand side. And there's also going to be 3.76 more nitrogens over on the right-hand side. So when you have an increase in the amount of air, and you call it out by a certain percentage of theoretical, you then have some other species on the right-hand side. Another way of calling out more air than you need is called excess air. And so this 150 would correspond to 50% excess. In combustion, there's also a final term that's used that's called the equivalence ratio. And what the equivalence ratio is the reverse. It's the fuel to air ratio. And so it's just the same thing as this, but inverted. And so it's the fuel to air ratio divided by the fuel to air ratio associated with the theoretical amount. And so this equivalence ratio then becomes a number that's either less than 1 or greater than 1. If it's less than 1, it means there's not enough fuel for that oxygen to oxidize. And so if it's greater than 1, then there's more fuel than what the air can oxidize. And so we would call one case fuel rich, and that's where the equivalence ratio would be greater than 1. And the other one is fuel lean, and that's where the equivalence ratio is less than 1. So different ways to define how much oxidizer we have for the fuel at hand. And so in the problem that we just did, if we had 50% excess air or 150% theoretical air, as I said, this 2 would actually become a 3. And because it becomes a 3, we then see that there's an extra oxygen that shows up. And because of this extra oxygen, we also have 3.76 more nitrogens that show up as a larger number here in the products. And so when we do these problems, the first thing we have to do is we have to balance the equation itself for complete combustion. And then if we are told that we have some extra air or some less air, we then have to modify the equation accordingly. And so after combustion is performed, a lot of times then what happens is if these products are brought out, a lot of times what will happen is they will remove the water, and so they'll condense the water out because this is just a gaseous species. They'll take these hot gases, run it through some cooling process, allow the water to condense, and then they can measure the amount of each of the gaseous components. And upon doing that, they then have a dry analysis of how much CO2, how much oxygen, and how much nitrogen were present. And again, it's due to the fact that they bring the combustion gases to the dew point, and we'll talk about the dew point in the next chapter, which is just the boiling point or the condensation point associated with the water in the mixture. Okay, with that, we will the next chapter, the next video, we'll talk about the conservation of energy for a reacting system. So we'll start now. What we've done right here is just balance the atoms. Now we're ready to balance the energy and figure out how much heat is released when this reaction occurs.